Okay. Hello, everybody. How's everybody today? Okay, very good. Let's go ahead and get started. Turn this on. And actually, before we get started on today's content, I was just going to point out, some of you may have seen this in the announcement that I sent, but there is an upcoming event, a datathon here at the U called Datathon for Justice. And I think it's going to be a really cool event. So it's going to be like, you know, a datathon, team-based, working on analyzing data sets having to do, well, socially relevant data sets. Excuse me. And there will be some preparatory workshops ahead of time, like an intro to Python and kind of an introductory data analysis. So anyway, I encourage you to check it out. I think you guys are a great fit for this event because you're clearly interested in data science. Okay, so why don't we get started now on today's content? Any questions before I get started? Okay. Well, today we're going to be talking about linear regression. So we'll discuss, first of all, simple linear regression, so the simplest case, and then we'll also talk about descriptive, sort of a descriptive statistics perspective of simple linear regression and an inferential perspective. And then we'll work our way up to multiple linear regression, which is a slightly more complicated model, taking into account more variables, and also nonlinear relationships or interaction effects. Okay, so go ahead and make sure you do the reading for today, which is from chapter 3 of an introduction to statistical learning. Okay, so what are we doing with linear regression? So in linear regression, we have an independent variable. Usually we denote this with X. It's often referred to as the explanatory variable. And then we have a quantitative dependent variable Y, which is often referred to as the response variable. So think independent, explanatory, those are synonyms, and dependent response, those are synonyms. And we usually think about X as influencing Y. So for example, as an explanatory variable, we might have square footage. And as a dependent variable, we might have house price, because the larger the house, the more it costs in general. We might have as our explanatory variable, dollar spent advertising, and as a response variable, profit. So the more we spend in advertising, the more profit we see. Or stress versus lifespan. I'm sure you can think of lots of examples. However, we might have, we could also have something like this, time spent studying as our explanatory variable, and our dependent variable Y, pass, fail. But why would this not fit into the context that we're talking about today? Yeah.
Because regression is like a gradual thing, like continuous, whereas that's discrete.
Yeah, essentially, close to that. Go ahead.
Yeah, we're seeing how changes in X affect like Y and how it increments or whatever in relation to it. If it's pass-fail categorical, then as time spent studying increases, like it's one or the other, and it can't like have a relationship, I guess.
Exactly. So with linear regression, for our response variable, we're thinking about something quantitative, not something categorical, right? Something that we're measuring, something quantitative. Well, it could be discrete. You know, that might, you know, if it's like you're counting something, you know, that's fine. But it needs to be a quantitative variable, not categorical, as you're correctly saying. There are other tools for categorical variables, and we'll talk about some of those later in the course. But for now, our response is going to be a quantitative variable. And then we've got a question in the chat. Are these readings required before class? It's not required that you read it before class, but I encourage you to read it either before or after class. Depends on your style. Some people like to see it before, some people like to see it after. Okay, so what is the context here for simple linear regression? Once again, we're going to assume that we have a sample, but unlike what we did before, our sample is now going to be a set of pairs, right? So we're going to observe in pairs where we have x1 value for the explanatory variable, y1 value for the dependent variable, etc. Okay, so we've got our paired observations, a y value going with each x value, and then we're going to model this relationship as a linear relationship. So if you might, for example, plot the data, plot y versus x. If you observe something like you see here in this figure, looks like a pretty linear pattern. So you might assume the model that y depends linearly on x. Here we'll use beta 0 to denote the intercept of that linear relationship and beta 1 to denote the slope of that linear relationship. Okay, so basically we're interested in computing some line that best fits the data, a line of best fit. And when we do that, we are actually going to approximate what the slope and the intercept are in that linear relationship. And so beta 0 hat will be and beta 1 hat will be the intercept and slope of the line of best fit. Okay, so we can think about y hat as being, those are the points exactly on the red line. Those are the predictions according to the model. And so the y values are the blue points, the y hats are the red points, which are given by this line of best fit. Okay, so you may ask, how do you compute that line? How do you actually compute that line of best fit? There's different criteria for what makes a line a good fit, but the classic thing to do is to minimize the squared distances to the line. And this is, so we're talking about a line of best sense in the least, a line of best fit in the least squares sense. And so if you want to minimize that squared distance to the line, you can actually work out the calculation. We won't go through the details, but this intercept and slope can be computed explicitly from the data with these formulas. We'll just use Python to actually compute what these lines are. Okay, but if you're interested in the math behind this, there's a little note in the repository in the folder from today, slr.pdf, that you can check out. Okay, so let's see how we're going to do this in Python. There's a number of different Python packages available for linear regression. Stats models, for example, scikit-learn, scipy. The functionality in scipy is a little bit more limited, so we're going to look at these first two, and especially the stats models one. Okay, so to kind of get us started, we're going to take an advertising data set, which is in the folder. And in this data set, there's basically 4 variables. We see sales, and then we see, this is advertising data. So it's listing in like 200 different markets. You can think of these as different locations, different cities for a certain product. How much money was spent in advertising via TV, via radio, via newspaper, and then what the sales were for the product. Okay, and we'll use linear regression to study the effect of advertising on sales. Did spending more money on advertising increase the sales as you would expect? Okay, so here, sales of the product is the dependent variable, and the how much was spent on TV, radio, and newspaper advertising is going to be the explanatory variable. Okay, so to get us started, we've got our imports, sort of the standard stuff. And special for today, we're importing this linear model from sklearn. And let's see, what else, anything else to point out? And well, yes, this stats models. Okay. So let's read in the data with our Pandas data reader. And here I'm just telling it to use the first column as the index column and when it reads in the CSV file. So we can take a look at what the data looks like, right? Here's our index, and then we see amount spent in TV advertising, radio advertising, newspaper advertising, and sales of the product. Okay, so let's take a look at a plot. That's always helpful when you're getting started to plot and describe the data. So here, we're gonna do 3 different scatter plots. For each, we're gonna plot the response variable or the dependent variable against each of these explanatory variables. So first we have sales versus TV, then sales versus radio, and then sales versus newspaper. And this is what we see. What do you notice about this plot? How would you describe the relationship between these sales and these different variables? Go ahead.
Oh,
Yeah,
oh,
I was trying to see.
my bad. So I feel like you tend to get more out of putting money into radio and newspaper, just because the line is more steep.
Right, so it does look more steep there, but also more scattered, probably, like both steeper and more scattered. So it's a little hard to know, like, you know, maybe which would be better, right, as an investment. It looks like more of a linear relationship for TV, but not as steep of a slope, indeed. And what you notice is like all of these high values, they're all TV. Like nobody is spending very much money on newspaper and radio. Like all of those are pretty low. And so the TV values are both like higher and more varied. So one thing that we can do just to kind of get some quick summary statistics is take the data frame and do our dot describe. And this just, you know, calculates mean and standard deviation for all of our variables. And so we can see indeed that in general, people are spending a lot more on TV advertising than newspaper or radio, but also that the standard deviation for that is a bit higher than the standard deviation for radio and newspaper. Okay. And also I should say, it's clear from the plot that these things are positively correlated. Like overall, we see this positive correlation in the scatter plot, not a negative correlation as we would expect. Okay, so, I mean, what do we really want to know though, when we're looking at this data? We want to somehow quantify the relationship between advertising and sales so that we can get a sense of, you know, is it linear? Is it some other kind of pattern? Ideally, we want to be able to predict, you know, if we spend more in this area, we're going to see this much increase in our sales. We want to make predictions along those lines. And we want to answer questions like, well, what should we spend our money on? Should we invest more in TV, radio, or newspaper advertising? What's the best strategy here? So which media is the most effective at generating sales? And then we'll get to this at the end of class. We may also be interested in how these things interact with each other. You know, maybe these things don't operate all in a vacuum, but there can be some interaction effects where if you're spending on, you know, TV and newspaper at the same time, somehow that's like the ideal combination. We'll see that a little bit later. But let's start, first of all, with the simplest model, which is just one explanatory variable and one response. And let's look at the effect of TV advertising on sales. That's the one where we pretty clearly see a strong linear pattern here. Okay, so this is going to be our model that sales is a linear function of the amount of money spent on TV. And we can run this linear regression with the sm.ols. OLS stands for ordinary least squares. And so when we call this, we just tell it what formula. Basically we want to predict sales in terms of TV. And we want to use the data in this data frame advertising. And we'll do a fit and then look at the summary of what that linear regression fit is. Okay. So when you do this, you're going to get, oh, hold on, I've got a couple chats. Let me check in with my online people. Okay, let me see. Is there a good way to ensure that you are not accidentally mistaking correlation with causation when using linear regression? There is not. That's a great question. And there is not a good way to do that. You have to look closely at how the data was collected and what the underlying process is. But just from the data itself, if you didn't know anything about X and Y, you would not be able to tell what the explanatory variable is and what the response is. Okay, and so, and this is a very good point, that basically what we're getting at today is talking about when things are correlated, but that doesn't necessarily say that one is causing the other, because we may have confounding variables. Okay, so when you run this linear regression, you're going to get a lot of output, which can be a little overwhelming at first. So let me highlight what are the most important things you want to look at. Well, the R squared value, okay, and that's right up there at the top. So you always want to check that. So that tells you basically how good the linear fit is. That's always going to be a number between -1 and 1. The higher it is in magnitude, the better the linear fit. And then another important thing in all of this output is these actual coefficients right here, this 7.03 and this 0.04. So these are telling you the beta 0 and the beta 1. This is the intercept beta 0, and that's the slope beta 1 in the linear regression model. Okay, so we can plot that. Let's take a look at this line of best fit. So first I'm just doing a scatter plot of the data in the normal way. And then I am using, so when you run the sm.ols, it's going to store the predicted values according to the linear regression, and we can plot them by just calling this ADTV OLS.predict. Okay, so here I'm just plotting the explanatory variable and those predictions from the linear regression. And we see the nice line. Okay, so now let's talk a little bit about what the values of, how to interpret the values of those coefficients in the linear regression. So the intercept of the line, beta 0, we saw was 7.03, right? So that's from right here, intercept. And then we saw the slope, 0.0475. And so how do we interpret, first of all, the intercept? Well, the intercept is when what? When you're not spending anything at all on TV advertising. That's the expected amount of sales you would have if you didn't do anything. And remember, these are in, well, actually, don't remember because I don't know that I said this, but these are in, everything is measured in thousands. So this is 7,032. So This means that without any TV advertising, the model predicts that 7,032 units of product will be sold. Okay, so, and the slope is 0.04. So how do you interpret these slopes? So the slope is telling you, if I increase X by 1 unit, what change do I expect to see in Y? So here, if I increase spending for TV by $1,000, what's the change I expect to see in Y? I expect to see again, this is in thousands. So if you multiply by 1,000, this is 47.5, that you sell an additional 47.5 units. Okay, so for every extra $1,000 that you're spending on advertising, you're selling an additional 47.5 units. Okay, and then how do we measure how good the fit is? So one way is to look at the sum of squared residuals, or SSR. So what is this right here? That's just Y hat, that's just the prediction. So we're looking at the true Y minus the predicted Y, and we're squaring that distance and we're adding it all up, okay? So you might expect if the line is a really good fit to the data, then this is going to be really small. Y and Y hat are going to be really close together, and this thing is going to come out to be a small number. Okay. So if this number is small, then the model fits the data really well. And let's see, we can access the quantity here by .SSR. And what is it? 2,102. What do you think? Is that small?
Can you show us the x-axis? Oh,
Can I show you the x-axis?
yeah, I just wanted.
Oh yeah, good point. Yeah. Okay, so I think what you're doing here is, you know, like show me the axes so I know like what the scale of the problem is, right? Because you really can't interpret this in any kind of universal way. It's going to depend on the scale that you're measuring in. It's going to depend on how many data points you have. So yeah, we want this to be small, but what we mean by small is just going to depend from example to example. So there is a way of turning this into a proportion that's more helpful for deciding if it's small or not. And this is what we do when we actually compute the R² value that we saw output in the linear regression. So that R² value, here we're writing it with a capital R², is an alternative way to measure how good of a fit the model is to the data. And the benefit is that it's a proportion, okay? So this takes values between 0 and 1. So it's easy to know if it's large or small. And so basically what we do, we compute the SSR. And so what is this? We're looking at Y minus Y hat squared. So we're looking at the variation that's not described by the linear model, because we're looking at that deviation. On the other hand, if we just computed the total sum of squares, and by adding up this is the variance of the response Y, that would be the total variation of Y. So what we can do is we can define R² to be 1 minus the sum of squared residuals over the total sum of squares. So you can think about, if we take this fraction, we're looking at what is the variance that is not described by the linear model divided by the total variance, and then we flip it around. So then we get the variance, the percent of the variance that the model accounts for, if you want to think of it that way. So what percentage of the variance in the data is described by the linear model, is captured by the linear model. Okay, so this is a useful quantity. And in our case, it was 0.61. So we would interpret that as 61.2% of the variance in sales can be accounted for by this linear relationship with TV advertising. Okay, so we've seen an R² value before. Do you guys remember talking a little bit about correlation when we did our introduction to statistics? So you may remember that we talked about measuring the correlation between two variables. And so you may be wondering, is this the same thing? And for simple linear regression, it is the same thing. Basically, what we're computing here by this proportion of the variance is the square of the linear correlation is the little r² that we talked about before. If we just computed the linear correlation between y and y hat, between the observed response and the predictions, that would be the r². The only reason we differentiate the notation here is that it's not exactly the same thing as we talk about more complicated models. So as we increase and we add more variables in, it becomes more convenient to think of it this way, as this proportion of the variance explained by the model. Okay. Okay, any questions so far? Okay, so let's just go over briefly how you would do this with scikit-learn. So this is just another way that you could run the same thing. So first, you would start off creating a linear regression object, right, by linear model.linear regression. And then I feel like it's a little bit more annoying if you're using the pandas data frames to do it this way, because it doesn't play nicely with the pandas data frames unlike the stats models that we did before. So if we want to do it this way, we have to reshape things. So here, what we do is we get the values out of the data frame, but then we have to reshape them. And this step essentially turns them into a NumPy array instead of a pandas data frame. And then that plays nicely with this linear regression function. Same thing for y. What's being done here? So if you look at this TV column in the pandas data frame advert, and you take the shape dot shape of 0, that just tells you it's got 200 entries in it. So it's just telling you to reshape it in the right size, which is 200 by 1. Okay, so then we're gonna do a fit, an LR.fit with X is our explanatory and Y is our response. And we can again make a scatter plot and also plot the predicted values, which are stored in LR.predict. That's quite similar to what it was before, but now evaluated at X. Okay, so let's do that. And so this is how we're storing the X values. I just printed that out so you could kind of see that they're formatted in a little bit of a different way. And then, but we get the same plot, same output, etc. Okay. All right. So now let's talk a little bit about hypothesis testing in linear regression. This is going back to a distinction that we've made before between descriptive and inferential statistics. So in descriptive statistics, we're just computing things. We're just computing quantities that summarize or characterize the data. And when we compute a line of best fit, that's really what we're doing. You know, what is the beta 0 and the beta 1 that minimize this quantity? That's just some computation that we can do from our data set. But the way of looking at this question from a statistical inference point of view would be to assume that we have a population, a ground truth population, and in that ground truth population, X and Y are related with a linear relationship, okay? That we really have some perfect linear relationship in our population, but we don't observe that directly. We observe a sample from this population that's noisy. So what we actually observe are samples, yi, which are a linear function of xi, but plus some epsilon I. So epsilon I here, you think of it as measurement noise, noise, uncertainty, yeah, things that make it hard to make predictions. We observe this noisy data. In the classic context, you assume the epsilon I are normally distributed, although in practice, they might not be. Okay, so, and then our job is from the noisy data, we want to figure out what beta 0 and beta 1 were in the population. So now we've turned this into a statistical inference problem where we've taken a sample and now we're going to try to make an inference about what the beta 0 and the beta 1 really were in the population. Okay, and that's just like what we did when we did the coin toss problem. So we had a sample proportion of heads, and we used the central limit theorem to say that the variance was like sigma squared over n. And then assuming that the null hypothesis was true, i.e. that we had a fair coin, we then computed the p-value by, calculating what's the probability, assuming the null hypothesis is true, that we would observe something as extreme as what we observe in our data. And it's going to be the same thing here. The same general procedure in terms of defining a null and alternate hypothesis, but this time they'll relate to the linear regression and then computing a p-value. So in this context, our null hypothesis would be that there is a linear relationship between X and Y. Sorry.
Yeah, I was going to say my notes say that there is no relationship. The null hypothesis is defined as no relationship.
Yes, that is
a typo?
correct.
Okay.
That is a typo. I'm sorry about that. Let me just fix that, and then I'll upload the fixed version afterwards so that you have it for reference. So the null hypothesis is there is no linear relationship between these. There is. Okay. Sorry about that. Okay. So the null hypothesis is that there's no linear relationship between X and Y. So the slope is 0 because there's no linear relationship, they're not affecting each other. The alternate hypothesis is that there is a linear relationship between X and Y. So the slope is non-zero in this case. Okay, so I don't really think you need to know the details here about exactly how we compute the p-value for this, but just know that it's the same general philosophy as what we did before. So according to, under the assumption that the null hypothesis is true, you compute a test statistic. And in this case, the test statistic will have a t-distribution with n-2 degrees of freedom. And then from that test statistic, you compute the p-value in the same way as the area and the tails from that test statistic. Okay. And so when we get a small p-value, what do?
Reject the null hypothesis.
Yeah, great. We reject the null hypothesis. And so in this case, that would mean that there is a linear relationship between the variables, right? We have evidence, strong evidence of a linear relationship. Okay. All right, so just to kind of drive home this inferential perspective, let's do a little experiment. So let's generate some synthetic data. So let's assume that this is what we actually observe, y equals 3x plus epsilon. And let's say when we take one sample, we'll see 100 points from this model. So we generate 100 random points according to the model y equals 3x plus epsilon. And epsilon here will have a normal distribution with mean 0 and standard deviation 2. Okay, and then from those points, we find the line of best fit. So we find the beta 0 and the beta 1 hat. And let's say we do this over and over again. Let's say we do this 1,000 times. So 1,000 times, we're going to take our sample of 100 points and compute the line of best fit. And let's see what that looks like. Okay, so I'm probably not going to go through this in too much detail because mainly I just want you to get the sense of what's happening here in this experiment. The red points are just one random realization of drawing 100 points from that model. And then each blue line is the line of best fit that was computed from one of the samples. So you see, this is a random process, right? For a different random sample of data, if we get a slightly different line, they're, similar, but they're a little bit different. So this is just illustrating that. Think about, this beta 0 hat and this beta 1 hat that we're computing when we run linear regression. Think of them as random variables, right? They're random depending on the sample of data that we got. And we will we'll do some statistical inference about their properties. Okay, so we can also then make a little histogram for all of the betas. So we see that, all of the beta 1s, all of the slopes. Definitely this distribution is centered at 3, which is good. It's targeting the right value, which was 3. But it ranges, from 2.4 to 3.6. Definitely in some of the samples, you get a pretty different value when you run the linear regression. Okay. So now let's go back to the linear regression model of sales on TV advertising that we did above, and let's find the p-values. Okay, so this was up here somewhere. Okay, so here we go. So what I pointed out before was the R squared, that's important. The coefficients, those are important. And next to each coefficient, you're going to see a p-value. That's this number right here, okay? So we have a p-value, that's the p-value associated with that alternate hypothesis that beta 1 is not equal to 0. So here, what do we see? It's 0, okay? Up to 3 decimal places, it's 0. So it's quite small, and we reject the null hypothesis, which means that there is evidence of a linear relationship between the variables. Okay.
To the right of that, is that
Yeah.
the 0.05 confidence interval?
Yes, then here is going to be a confidence interval for that value of the parameter. So you can sort of see, basically adding in a margin of error, you can be, well, we know maybe it's not exactly 7.03, but we're pretty confident that it's somewhere between 6 and 7.9. Yeah. Yeah, so this should be, I guess, a 95% confidence interval based on what's up here. Okay. Okay, so let's see. Let me do a little time check here. Why don't we go ahead and take our 5-minute break, and then when we come back, we'll take a look at analyzing the other explanatory variables, and then doing a more complicated model where we look at everything together. Okay, so let's come back at, I guess, 426.
Anna,
Yeah,
can I ask a question about something from lecture 7, just to clarify something? While we have a few minutes.
of course.
So in lecture 7, when we were looking at like a two-tailed z-test
Mhm.
versus like a one-tailed test, in the code for the two-tailed example you gave for like the polio vaccine,
Yeah,
you divided the p-value at the end, the last line of code.
right.
And I was
Mhm.
just wondering why, like, why do we divide the p-value?
I divided the p-value in that example because if I'm remembering correctly, the
Mhm.
alternate hypothesis was one-sided. So it was something like the proportion for vaccinated is smaller than the proportion for unvaccinated. And but the code, when you run it, it defaults to a two-sided test. So it defaults to an alternate hypothesis that's just those proportions are not equal to each other. So if your alternate hypothesis says that, one thing is not equal to the other thing, then that's fine. That's how the default goes. But if it has a greater than or less than statement, that's a one-sided test. But that is easy to compute because it's always half of the value of the two-sided test.
Okay, so is it best practice if we're doing like a one-sided test that we have to divide the p-value? But if it's
Yes.
a two-sided test, then you don't divide the p-value.
Yes, that's right.
Okay, because you have a p-value, it's like on either side of the histogram, but for a one-sided, you're just thinking about it on one side of the histogram.
Exactly. The default is to compute the area in both tails, looking at both the probability of getting something like, smaller and also the probability, both the probability of getting something really small and the probability of getting something really large. That's the default. But depending on how your alternate is set up, you might just want to calculate, the upper tail or the lower tail probability.
Okay, so best practice if it's a one-sided is that you are going to divide your p-value, but you should consider your alternate hypothesis.
Yes, and depending on the function and the software, you might be able to just tell the function like run this as a one-sided test, specify the alternate hypothesis when you run the test, but I'm not quite sure. I'm not quite sure what the syntax for that is.
Okay, well, no, that's really helpful. Thank you.
Yeah. Mhm. Any other questions while we're waiting around? Okay, all right, well, let's get started again. So now let's kind of repeat what we did, but looking at the other variables, right? We also had advertising with radio and advertising with newspaper. So here, let's do again with this .ols function, we'll do a linear regression of sales. Again, this is the right syntax. So this is saying predict sales as a linear function of radio, and then we'll fit that linear model. Okay, what do we see? Not nearly as good of an R squared value. This is, I mean, it's, you know, it's something, but it's not real high. So about 33% of the variation in sales can be explained by this linear relationship with radio. And now we can also see the coefficients for this model, and the p-values, though, are still significant. Okay, so this is still significant according to this test. Okay, let's try it with newspaper. It's getting even worse, right? So now we only have an R squared of about 5% of the variance explained by the model, but still we are getting that the relationship is significant. So this is kind of interesting, right? It's definitely possible that when you run a linear regression like that, you get a very bad R squared. You don't see a very strong correlation, but it still comes out to be statistically significant, right? There's still evidence that there's some kind of relationship there. So having a small p-value, but just be careful with how you interpret that. It doesn't mean that that relationship is strong. It doesn't mean that necessarily it's going to be a close linear relationship. Okay, and so here we can, again, plot all of those things just like before, do a scatter plot, and then on top of the scatter plot, just go into and with the dot predict, pull out the predicted values, the y hats, and plot those as well. So we see the TV regression line, the newspaper regression line, and the radio regression line. And as you guys correctly pointed out in the beginning of class, right, these have steeper slopes, but lower R squared than the TV. Okay, so let's think about how to do the interpretation. So I don't know, what would you guys say after everything we've done? Could you answer the question, what's the most effective way to spend your money in advertising? Somebody votes for radio. Would anyone argue with that?
They kind of all fill up with 50,000 in it, but there's a reason that they do that. I feel like they did the estimation returns after that, like 50,000.
Oh, you mean like the line is not plotted past there? Yeah, I mean, the reason it's not showing past there is just that's the largest y hat that we got, because remember, we're plotting this as a function for every x value in our data set. We are evaluating the y corresponding to it, and we didn't have any values for radio that were over 50,000.
Yeah.
So we just stopped there. Indeed, what would happen if we kept going, that is hard to say. Yeah, but radio definitely has an impressively steep slope. So that is tempting. But at the end of the day, it's kind of hard to answer this question because we're looking at these things one at a time, right? We're looking at these individual linear regressions, but more generally, they could impact each other. Like, what if we looked at everything all together and tried to make a prediction? So it can be a little hard to answer that question when you run all of the regressions separately, but generally a better thing to do would be to come up with a more comprehensive model where this is called multiple linear regression, where we construct a model in the following way. Sales, is again linear in each of these variables. It's linear as a function of TV, linear as a function of radio, and linear as a function of newspaper. So this is still a linear function, but it's a linear function with multiple variables, right? And so now we have 3 different slopes, one associated with each variable in the model. Okay, so let's try this. Multiple linear regression. We can run it in the exact same way as we did before. Now we're going to try to predict sales as a linear function of TV plus radio plus newspaper using all 3 of those explanatory variables at the same time. And what we notice is, given access to all 3 of those explanatory variables, we can make a much more reliable model, right? We can get a better fit with the Y values. This is expected. The more information you throw at a predictor, the better it's going to do. So here we see the R squared value increase to about 90%. Okay, so, and then again, so here when we're looking at this output, we've got an additional, we still have p-values associated with each of these coefficients. Then we have a p-value. This is also a p-value right here that's associated with sort of running one hypothesis test for this whole thing. Actually, hold on, let me go a little further because I think it's written up a little bit more clearly right here. Okay, so the interpretation for the slopes is still the same. Let's look at the slopes here. Here are the coefficients, here are the slopes. So according to this model, if we spend an extra $1,000 on radio advertising, we expect sales to go up by 189 units. If we spend an extra $1,000 on TV advertising, we expect sales to go up by 45.8 units. So that's a similar number as what we had for TV before. I think we had like 47. For radio, actually, I forget what it was for radio. Let's see. For radio, it was... see for radio here, 202. So yeah, it's similar. So they're similar to what they were for those individual ones, but they are different. And for newspaper, it was, yeah, so this one actually changed a lot, right? For newspaper, when we did the one-on-one regression, we got a slope that said if we increase spending by $1,000, we'll increase sales by 54.7. Now, if we look at the slope that we get here, it's like 0. It's saying that it really won't do anything. Okay, so that's very different in terms of the interpretation that we draw. When we include all of these variables in the model, it's saying that, spending more money on newspaper advertising is not going to help you. Okay. But it's also helpful here to look at these p-values. And so we notice that for TV and radio, they're significant, but now the p-value for newspaper has gotten really large. So when we did the model incorporating all 3 of these variables, the p-value looking at the coefficient for newspaper got really large. Okay, so this sort of confirms radio is the most effective method of advertising in terms of the most bang for your buck. And what it's doing is running a hypothesis test, in this case called an F-test, with a null hypothesis that all coefficients in the model are 0. So there's like one global hypothesis going on, which is saying as a null hypothesis, all coefficients are 0. There's no kind of linear relationship between anything. And so when there's a small p-value for this, it just means that there's some kind of linear relationship with at least one of the variables there. But then you can look more closely at the output for the p-value for each individual coefficient. Okay, so like we saw, the p-value for radio really increased up to 0.86. And so we would say that there's not sufficient evidence to reject the null hypothesis that the newspapers and sales variables have no relationship. That is like a long way of saying, okay, what's the conclusion when we have a large p-value? We don't have evidence for the alternate hypothesis. So we don't have evidence of a linear relationship between the newspaper and sales in that case. Okay, so why do you think this happened? Why do you think when we ran it one-on-one, we got a significant result, but then when we ran it with all three, it becomes insignificant? Maybe nobody wants to answer because maybe it's already written up there, I don't know, but it's in this case, one thing that can be, hold on, let me see if anyone put anything into the chat. Okay, yes, we are able to consider confounding variables. So indeed, so this may be a case of confounding variables. So one thing that we can take a look at is what is just the linear correlation between these variables that we're looking at in the data set. And you remember from our previous lecture that this is how you define the linear correlation between two variables x and y. You add up, this centered xi times the centered yi, and you divide by the standard deviation of x and the standard deviation of y. And this will always be a number between -1 and 1, which measures how much the two variables vary together in a linear way. Okay, so let's take a look. For this data set, what are the correlations between these variables? So along the diagonal, you'll just get ones because you have perfect correlation of TV with TV. But then here we see a correlation of 0.05 of radio with TV, and we see a correlation of 0.35 with radio and newspaper. Okay, and so that's not like a real strong correlation, but it's a weak to moderate correlation, maybe a medium correlation. So it may be hard to really distinguish what is the effect of spending money on newspaper ads when we have this correlation with radio. So when we see, when we run our linear regression of sales versus newspaper, it may be hard to detangle, okay, how much is, newspaper affecting things and how much is it that newspaper is just correlated with radio, and radio is a really good predictor for sales. So it can be a little tricky to make these interpretations because of all these correlations. Yeah.
Just double checking that the TV, radio, newspaper are just columns in this data frame.
Yeah.
Okay.
And so is sales.
Oh, okay. And sales.
Yeah, all these are the 4 columns in the data frame. And so when you do this advert.core, it's just going to do a little matrix computing the correlation between all of the columns. Yeah. And then this little scatter matrix is also helpful. So it's doing that same pairwise comparison, right? So this would be, this entry right here would show you a scatter plot of TV versus radio. That's really, really bad correlation. Then here we can see the scatter plot between newspaper and TV. And again, we see this strongest sort of linear relationship with TV and sales. And then on the diagonal, it's just going to do like an estimator of the histogram of that variable, or of the density function of that variable. Okay, so what we see is we do see a correlation between newspaper and radio. And so it can be hard to distinguish the effects. So the influence of radio on sales can be incorrectly attributed to newspaper advertising, but by doing a model that incorporates all three of those variables, that's less likely to happen, right? If we include all of the variables, then the model will be more able to determine which are the best predictors on their own right. Okay, so because when we ran the linear regression with newspaper, we got such a horrible p-value and it didn't look like it was a very helpful predictor, a better model would be just to leave it out, right? If a variable is not helpful, then just leave it out and redo the model. So a better model would be to just predict sales and include just the TV budget and the radio budget. So let's redo that with the two predictors. And here we see, again, an R squared of about 90%. So we took that one variable out and it didn't change the R squared, right? Our R squared is still as good as it was before. And our model is simpler. And now in this simpler model, we see that both of our variables are significant, have significant coefficients. Okay, so it's working pretty well. It accounts for 90% of the variance in the data. And this here, I'll let you, look through this probably after class if you want to kind of parse the code, but it's just making a surface plot of the data. So now what do we have? We have a response variable y, which is the height of this surface. And we have two explanatory variables, which is TV budget and radio budget. So think of this as like a plane, right? This is like a little surface here. And you can plot that with a surface plot with a plot surface function. Okay. Okay, so nonlinear relationships. Actually, maybe more appropriately should call this section interactions. So let's say that we want to consider the possibility that somehow what we budget for TV and what we budget for radio, like there may be some kind of interaction going on. One generalization of the model that we could do would be sales is beta 0 plus beta 1 times TV plus beta 2 times radio plus beta 3 times TV times radio. So here we've added a third variable, which is the product of these two variables. When we have a variable that's the product of two other variables, it measures the interaction between the variables. And so here, the idea is that, yeah, maybe when we spend X on TV and Y on radio, the benefit to sales, maybe it's more than X plus Y. Maybe we get like some extra synergy by doing both of these things that increases the sales more than just doing them individually and adding the effects. Yeah.
So would it be like realistic to try out TV budget squared, like radio budget normal, like, I mean, multiply together? Is that something you would ever want to test? Yeah. There's definitely, yes. I mean, you could, if you have some reason that you think
yeah, that your model might kind of depend on the square of a variable. You could do that transformation to find a new variable and then run the linear regression. Yeah, that's a very valid thing to do. Right, so once you start thinking about this, yeah, there's so many things that you could, there's so many things that you could do. But this one of sort of these products of variables that are already there is a real classic way of measuring interaction, you know. Even like in like predator-prey models, if you want to think about how certain populations are going to change, well, it's going to depend on, you know, the product of how many foxes you have and how many rabbits you have, because it depends on how much those populations are coming into contact with each other. So sometimes interaction is important for the prediction you want to make. Okay, so, I mean, and here, I guess we don't know, but it's a reasonable thing to try. Let's try it and see if we get a good model. So we're going to redo it. Now we're going to have TV radio and TV times radio. And we can run this, and we actually see that including that interaction term seemed to give us a nice little boost in terms of the fit. Yeah.
So when we're multiplying them together, is that like multiplying each entry? Or is it
multiplying each entry? That's right. So another way that we could do it is we could have like gone up to the data frame in the very beginning, right? And just made a fourth column. I'm trying to see where did I show the data? Ah, here it is. I mean, yes, it's literally like making another column here. And for each entry here, we just take this number times that number. And then we could just run a linear regression with radio, newspaper, and new variable, right? We would get the same result. But the function is built in to do that for you, so you don't have to do it. Okay, so back. We're on interaction. Okay, so we get a nice boost in performance. Now it's closer to 97% of the variation in sales described by the model once we include that interaction term. Okay, and then here, this is our global p-value, very small, indicating that there's something significant going on. At least one of the coefficients is significant. And then we can look more closely at the individual coefficients here and their p-values. So that's in this column right here. And we see that they're all significant, right? The interaction is significant. Radio and TV all have small p-values. Okay, so we finally gotten a really excellent model with an R-squared of 97% and all coefficients significant. And so we can, once again, do the same surface plot. If we want to visualize, it may be a little hard to tell the benefit of this one over the other one just from the plot, but you may see that, well, what do you see actually? You see that it's not a completely flat surface anymore. So this interaction term has changed it to curve a little bit. And this seems to be a little bit of a better fit for this data. It's not totally flat. Okay, so this may seem awesome, and you may be thinking, okay, let's square the variables, let's cube the variables, let's do all of these combinations, and let's include all the variables that we have, and surely we'll get a very good model. And indeed we would, but you don't want to overfit the data, right? So we'll talk more about that later. But in general, what do you want to do? You want to make a really good model, but you don't want to make it too complicated, right? You don't want to use more variables than you need or make it more complicated than you need. So as you can see, from the same set of points, you can do all kinds of things. And some of them, like this one right here, fits the data really well, but is going to be a terrible model, right? It's fitting every single little noise in the data. Okay, so that is the end of what I had today. Okay, we still have 10 minutes, so that's great. why don't we use the last 10 minutes for our activity? So you may not finish it, but there is some extra, there's exercises inside the lectures folder with a little example for you to try out running the linear regression. So in the last 10 minutes of class, I'll let you play around with that and answer any questions that you have. Okay, any questions before I start the breakout rooms? Just some people exiting so they're not forced into a breakout room. Okay, that's okay. So let's see, for 20 people. Okay, let's do 7 breakout rooms. Okay. Okay, and you guys can talk to each other, right? So maybe you guys can find a partner or two and just take a look at the example in the last few minutes. Nope. Right, so just so everyone is on board, this is the one called activity.
So if you're just doing like one versus one, the big one is the bars. Okay. So they're the same thing. So they just did not do it. But I can't remember exactly. Okay, what the adjustment is. So if you're just looking at like what is the R squared value, then I would just point something. Are you good? You have any questions?
Yeah, I'm all right so far. Registered this, but I don't know what
Yeah, so you kind of reformat it a little bit, because what do you want? You want like a whole vector of the x values and a whole vector of the y values, right? All in like one long thing. So putting the y values together, you could do just like concatenating them. I think actually we did. Right? Yeah. But here, you need it like 0, 0, 0, 0, 0, and 2, 1, 5, 2, 1. Yeah. You need to repeat it for as many times as elements you have in that list.
Is there a better way to do that?
Then, not that I know of. So, I mean, one way that you can do like 0 times 10, and that'll make it into like a list of 10 times that thing, or if you're familiar with that little trick.
It's like 0 like in brackets, or just a normal 0?
So like if you do 0 in brackets and then times the length of, food consumption of 0. Yeah, and the same for the other ones, that's going to repeat it, but I don't think they're going to be, so it might be inside the same list. So you might have to use concatenate to put them together, but that's the idea. Yeah.
So happening is
That's right. So think about for each one of these, it has an x value, which is 0, 0, 0, 0, 0. Right? The x value is the same for all of those values of y. Yeah, these are all the y values. And so all of these share the same x value, which is 0. These share the same x value, which is 2.5. And these share the same x value, which is 5.
Oh.
So, but you do need to create a list that repeats that, however many times the length of the list is. So I think you will need to concatenate those things because this is going to be a list of lists. And I think it'll yell at you for, I think you want one list with all of those things. So I think you want to say why is concatenating those things. Does that make sense? Yeah, so you just want one list with all of your y values. And so if you take these 3 and you just concatenate them, you'll get one list of all of your y values.
But I'll just try to. Okay.
Does that make sense?
Yeah, makes sense.
Okay.
Thank you. Just.
For example, like a so that, yes, you did a histogram, so that's good, and you get some sense of it, but the normal probability plot is that the dots in the line. Okay. Yeah.
I'm gonna try something. You should tell me.
Yeah. Okay.
Yes, I overheard what you said in him, but that's what I knew.
Okay, great.
Okay, I need to put this in.
Yeah, maybe you should go talk. That's it. I feel a little short on time, but.
Yeah. Thank you.
Okay, and yes, it's after 5, so of course, feel free to leave anytime. I'll see you on Thursday. What's funny?
Tuesdays and Thursdays are fun. It's like nonstop data science and coding from like 9:40 in the morning until 9 at night.
Oh my.
Because my partner and I meet in between classes. It's fun.
Tuesday, Thursday, day to day.
Thank you so much.
Yeah, you're welcome.
I've always wanted to go over multiple linear regression. I was doing an assignment for my other data class last week, and I was like, man, I really wish I knew how to do this. And now I
That's
do.
so encouraging to hear, actually. That's very nice. Okay, I think everybody has left our rooms, so I can close them out. What's that?
Because the issue I face is that there's no, it says there's no alternate SK1, even though I feel like I don't know.
Yeah, I think you wanted, I do think you wanted imported it as. Let me. I don't know, the imports in there though, right?
It's, the issue was that the module isn't found like this. Because I don't know if it's even installed on the platform, so I hit that just now, and then it still doesn't work. So at this point, I did a flip install, but I don't think that should be an issue. I'm gonna fix it.
I'm not sure you're in the right, like, two versions.
Yeah, I'm using Python 3.8, but it works with 3.8, so
I think we're using 3.17.
3.97.
Yeah.
Okay.
You might want to
Okay.
make sure that you're using the same version, just so that if there's anything like that in the future, you know,
Yeah.
because I don't know. I'm not quite sure.
Did you get it? It's installed in Amazon, but I think okay, let's check it out.